Hello, welcome back to Calculus 2. In this video, I'm going to describe a few of the main ideas of calculus in general, some ideas that you've encountered in prior calculus courses, and some that we'll encounter in our course moving forward. And I'm going to briefly describe how they all tie together, and that's really what we're going to explore over the next few videos together. Now, I have to state that the image you see, or the few images you see on the screen here, and the main ideas of how these problems are outlined in the three problems that you see listed here, these ideas come from Stephen Strogatz and his book Infinite Powers, How Calculus Reveals the Secrets of the Universe. I highly recommend this book to anybody watching this, whether you be a student who's just learning calculus or a fellow teacher who is looking for new ideas to use in your courses. I really enjoyed reading this book. It gave me an interesting perspective on some of the main ideas of calculus and made me think about them in new ways, and also taught me a lot about some of the modern applications of calculus that I didn't know anything about. But one of the reasons that I really enjoy this book is that Dr. Strogatz outlines these three main problems that have historically motivated a lot of the work in calculus. And he spends some time in the book, and we're going to spend some time over the next few videos learning about how they're all related to each other. So here's what I mean by that. There are three central problems in calculus. The forward problem, number one, is the one that you really learn about in Calculus 1 when you learn about derivatives and slopes of tangent lines and things like that. Given a curve, like this graph of a function you see right there, find its slope everywhere. In the sense of, if I were to give you a function or a curve, and I were to give you a particular point on that graph, on that curve, the goal would be to find the slope of the curve right at that point, or the slope of the tangent line at that point. That's the so-called the forward problem. Given a curve, given a function, can we discover what its slope is anywhere? And that's exactly what a derivative represents, and you can see the little notation there, dy dx, for a derivative. Now, problem number two is essentially that exact idea, but backwards, so he calls it the backward problem. And instead of being given a curve and asked to find its slope everywhere, the backward problem says, suppose I was given the slope of a curve everywhere. Could I go backwards and rediscover what the curve must have been? So in other words, if somebody gave me perhaps another function that represents the slope of some curve, could I use that given function to discover the original function, whose slope everywhere is the function that was given to me? Now that might seem like a strange thing to do, but I hope that at least naturally, once you learn about the forward problem, you might wonder, could I do that backwards? And I encourage you to ask questions like this, at least of yourself, and of the books you read, and of your teachers in mathematics courses. When you do something, think about at least, and perhaps ask out loud about, could we do that backwards? What's the reverse look like? Is that equally challenging? Is it a harder problem? Is it an easier problem? What kinds of applications could that lead to? Just try to encourage your brain to think like that. But right now, I could totally understand why, trying to solve that problem seems like an odd thing to do. So let's move on for just a second, talk about problem number three, the area problem, and then we'll discover how they're related. The area problem says, given a curve, like the function we have graphed over here, and two particular points on the curve, let's say like this one and this one, could we discover the area under the curve between those two endpoints? And that's what this shaded gray region in there is. Now that seems like at least a more natural question, at least it's something visual that I can draw. And it's also what we spent the last few videos motivating, how I described that if this function, the curve given, represents the velocity of some moving object, we've just learned about how the area underneath that curve represents the displacement of the object. In other words, knowing how fast an object is moving, the area under the graph of that function tells us how far the object has moved. And so now's when I get to reveal that you learned about problem number one, the forward problem, in Calculus 1. That's exactly what the derivative is. And over the last few videos, we've motivated problem number three, the area problem. And in the next few videos, we're going to talk about how problem 2 is in fact exactly the same as problem number 3. I only have my audio here, so you'll have to trust me that I'm making a big surprised face, because I still get amazed by this, and I'm hoping that you're astounded by this fact too. That somehow the backward problem, which, again, admittedly sounds like a very odd thing to do, that turns out to be exactly equivalent to finding the area under the curve. It's the same as the area problem. Well, let's build up to that. I'm going to take a couple of videos to fully describe that. So let's move on and talk about something that's closer to what the backward problem is about, and then we'll see how it's connected to the area problem. Now let's talk about derivatives and really the inverse, the opposite, the backwards version of that, antiderivatives. Now you see here I have a label here when I teach Calculus 2. Specifically, we have a worksheet of derivatives that we talk about on day 1. So don't worry about that. Just take this function. The question I asked on that worksheet was, given this particular function here, f of x, first of all, just practice finding its derivative. So that's what I see down here. I hope you know how to find that, specifically for a polynomial function like this. The power rule states that if the function I have is a power of x, like x to the n, then the derivative of that, f prime of x, it says drop the exponent in front and shrink it by 1. And other rules we have are, for 4x cubed, the derivative of that is going to be 4 times the derivative of x cubed itself. So when I apply that here, the 3 drops down, and 3 times 4 is 12, and then the 3, the exponent, shrinks into a 2. And similarly here, the 2 drops down, 2 times 2 is 4, the 2 shrinks to a 1, and I have x to the 1. And then a derivative of a constant is 0. Another way to think of that is 1 is like x to the 0. So when I take the derivative of that, it's like the 0 drops down in front, and I end up with nothing. Another way to think of that visually is if I have the graph of the constant function 1, what is the derivative of that? Well, it's supposed to be the slope of the curve, and that flat horizontal line has a slope of 0 everywhere, and so that's why its derivative is just 0. Okay, so that was central problem number 1. Find the slope of a curve everywhere. Central problem number 2 is essentially asking for an antiderivative for us to go backwards, or in other words, to address this follow-up question I asked, which is, can you find a function, let's use capital F to distinguish it, can you find another function whose derivative is that first function I gave you, little f? And this may have required you to turn your brain around and think in a different way, but I'm hoping that if you look at the statement up here about derivatives of powers of x, you can think about how to kind of reverse engineer this and come up with the function capital F that you see down here. Think about if I started with a term like x to the 4th. Its derivative is going to knock the 4 down and decrease it to an exponent of a 3. That's exactly what I had in the original function up there. Or something like this term, when the 3 drops down and I take a derivative of it, the 3 times 2/3 gives me a 2, like I see there, and the exponent 3 will shrink to a 2, like I see there. And so, if you check term by term, this is indeed a function whose derivative is that. In other words, if I take the derivative of capital F, I will end up with the function little f. Now you also see this plus c that I have written at the end there. And that stands for an arbitrary constant, a random real number. Because essentially that value c could be anything. It could be plus 5, it could be minus 100, it could be plus 2 pi over 78, whatever. But the derivative of any constant is 0. So no matter what that number c is, its derivative of the whole function will end up being exactly this. X to the 4th goes to that one, 2/3 x cubed goes to that one, x goes to that one, and c will go to 0. So it's like having a plus 0 at the end. So in fact, this means that the solution to central problem 2 here has infinitely many answers, but they're all kind of the same. They're all this function of terms plus or minus some constant number at the end. So I have written down here the one where c is 0, just to have a specific example in mind. And now let's formally define that term. When I say antiderivative from now on, I mean this kind of thing we just did. Given a starting function, which we'll often represent as little f, its antiderivative, I'm going to use a capital F often to mean the antiderivative, and it's a function whose derivative gives me back the function little f that I started with. And we'll often write it in this general form where it could be some formula of terms plus some arbitrary constant, c. Now, there's actually a visual interpretation of that c term. So just let's return to a specific simple example. Let's start with the function little f equals 2x. Well, if you reverse engineer the power rule, you'll realize that the derivative of x squared is 2x. So in this specific simple example, an antiderivative would be the quadratic function x squared. And that's what I have graphed in the picture down below. If you see the red curve right in the middle of all of those, that's the function x squared. And it's the antiderivative of 2x in the following sense. If I were to choose a particular x value, and I were to go up to the corresponding point on that curve, x squared, and I were to ask for the slope of the curve there, if I were to ask for the slope of the tangent line at that place, let me try to sketch that like something like that, then the slope of that tangent line is exactly 2x, 2 times whatever the x coordinate is of that point on the curve. That's the sense in which the derivative of x squared is 2x. Or in other words, the antiderivative of 2x, one such antiderivative is x squared. But if you look at all those other curves that I have graphed there, the blue one and the green one and the purple one and the black one, they're all basically the same shape. They're all the parabola y equals x squared, but they've been shifted up by 1 step, or maybe down 2 steps, or something like that. They're all the same shape, but they're slid up and down the y-axis. I'm not bending the curve in any way. So by shifting them up or down, I'm not ruining this fact about how the slope anywhere is exactly double the x-coordinate of the point. Right? If I zoom in on a corresponding point over here on the green curve at the same x-coordinate, it has the exact same slope of a tangent line. That green line is parallel to that red line. And so it has the same property that the slope is double its x-coordinate. It's just happening a little bit higher up, but that means it's a slightly different y-coordinate, but I haven't changed the x-coordinate at all. And so one way to think about this is f of x equals x squared plus c. It captures not just the one curve that obeys this property, but it captures all of them that have this particular shape. And oops, I just see something got cut off there. It captures all possible graphs with that shape. And here's a way to visualize that using Desmos. What I have graphed here is the function 2x. You can see that in line 1. And what I've started to type in line 2 is x squared plus c, and I can type that capital C there. And you'll see that it says I have too many variables, try defining c, or right underneath it says add slider. And if you tap that button, it creates a slider that I can move back and forth and adjust that value of c. Now, just to have something to compare to, I'm going to have y equals x squared itself, just sitting there as something basic to compare against. And look at how as I change that value of c, it's the same curve, but moved up or down. So here I am moving it up a few steps, and I'm moving it down a few steps. But at all points in time, at all x coordinates, at all points left and right, that curve will have the same shape as the basic x squared curve, the green one. That's what I'm describing on this slide here. Now here are some practice problems, and I encourage you to pause the video here for a few minutes and to try each of these. And I'll say that some of them are meant to be a challenge, and if you can't come up with an answer after a couple of minutes, that's okay. Unpause the video and I'll go ahead and talk about all the answers, but I think you will gain a lot from at least making yourself think about it, trying to discover something, and even if you don't figure it out on yourself, that's totally fine. Just come back and listen to my description of the solutions in a minute. Okay, let's talk about these answers one by one here. I meant for the first two to be relatively straightforward applications of that same power rule idea I was describing on the previous slide, or 2 slides ago. Both of these employ the power rule in reverse, let's say. I'll just call it reverse for now, because I'm thinking about the backwards problem number 2. I think the first example is a lot more like the problems we were doing earlier, and problem number 2 here just requires you to remember, in case you didn't, that x to the 1/2 I can always think of as an exponent. Sorry, how I just said it. Square root I can write as x to the 1/2. Any root function I can always express as an exponent. And so just as another example, remember that the cube root of x is x to the 1/3, let's say. Or something like x to the 3/2. I can write that as the square root of x cubed. The 1/2 part giving me the root, and the 3 in the top giving me the cube part. So that thing I could also express as root x all cubed. Those are all the same thing. And so I'm using that idea here. If I think of my starting function as x to the 1/2, then when I increase that exponent by 1, 1/2 plus 1 is 3/2. That's where the 3/2 power is coming from over here. And then if I think about taking the derivative of something like that, if I were to take the derivative of x to the 3/2, the power rule would say take the exponent and drop it down in front. And so I would get a 3/2 out in front. And then it would decrease down by 1, and it would give me the 1/2. But that 3/2 dropping down in front is why in my answer I have the reciprocal of that, the 2/3, to kind of cancel out the 3/2 that's going to fall down. And so in fact, I think I can express up here a general rule, which is x to the n. If I ask for an antiderivative, it's going to be increasing the exponent by 1, and then dividing by that exponent, or multiplying by its reciprocal, as the case may be. Just fix that 1 there. And so that's really the fact that I'm using here. X to the 1/2 became x to the 3/2 divided by 3/2, or in other words, times 2/3. Now, question number 3 here, I've meant to be actually the one exception to that rule that I just stated. So think of 1 over x as x to the -1, as a power, as an exponent. And if I try to naively apply this antiderivative power rule that I just wrote down over here, you actually end up with a big problem. If I think of n as -1, then what happens when I get to this part here and I try to do 1 over n plus 1? If n were -1, really, then I would have 1 over -1 plus 1 is 0. I would have division by 0. That wouldn't make any sense. That's undefined. And so this thing that I wrote down here actually needs to take this qualifier that says except when n is -1. I'm not allowed to apply this antiderivative rule when n is -1. I have to do something different. And this is where I was really just asking, do you remember that the derivative of natural log is 1 over x? That's the fact I need to know to remember that the antiderivative of this is natural log of x. And this is something that, if it's not right on the tip of your tongue now, hopefully after a couple of times of using this, it will be more readily come to mind. But this is something that we just kind of have to know. Now, the other thing that you might notice is that I put these absolute value bars, just because you'll probably see this if you ask a symbolic calculator for this answer or look up in a table of antiderivatives. And the whole idea behind that is it's really the same answer. If you wrote natural log of x like I have here, I would know what you mean, and I'm not going to take off points or whatever. I'm putting big scare quotes around that in case you can't see. But it's really just to essentially give the same answer, but with the widest possible domain as possible. So the the 1 over x function is defined for all real numbers x except 0. That's the only place it's undefined. But if you think about the natural log function itself, ln of x, that has a much more restrictive domain. The y equals ln of x function looks kind of like this, because it's undefined for x equals 0, but also for x being negative. And so by putting those absolute value bars, it just says, you know what, if I have a negative input, I just want to take the absolute value of it first, and then output the same value that ln of the positive number would have done. So in other words, just take the mirror image of that curve across the y-axis and include that as part of the graph. So both of these two curves are part of y equals ln of absolute value of x. And so that's what I mean by extend the domain, so that now this answer is defined for the very same values of x that the original function we started with, 1 over x, was defined. All right, so that's that one. Number 4, I really meant for this to be another one of those just know that we know this. I need you to have on the tip of your tongue that the derivative of the arctan function, the tan inverse function, is exactly this thing that we're facing. I'm sorry, but this is just kind of something that we have to remember that we know. The derivative of the arctan function is this rational function, this ratio of polynomials, 1 over 1 plus x squared. And I assure you this is going to come up quite a bit because of how interesting it is that a arguably more complicated function, an inverse trigonometric function, its derivative is somehow a nice fraction of polynomials, a nice rational function. Because of that, we're going to see arctan appear quite a few times in this course, probably more than you're used to in previous math courses. Now, with problem number 5, I really chose this one to demonstrate an interesting general fact about antiderivatives, which is, sorry, they're kind of challenging. They're just plain hard. They're harder than taking derivatives. In other words, the backwards problem is much more challenging than the forward problem. When you learn about derivatives and the chain rule and the product rule and things like that in Calculus 1, you're essentially being taught how to take the derivative of all possible functions. If you know the chain rule and the product rule and you know the derivatives of the basic functions, you can take the derivative of any combination of those functions by just plugging and chugging, by just applying the rules in the right order. There's no art to it, really. But the backward problem is truly an art form. It requires much more intricate thinking. And with this example, I'm showing you how changing one little thing, like the 1 in the top of that fraction becoming an x, in terms of the forward problem, taking a derivative, this would make it more complicated, but not that much more so. It would just take a few more steps, but it would fundamentally be pretty much the same thing. But here, asking for an antiderivative, doing the backward problem, this is a completely different question, even though it looks superficially very similar. And so if anybody came up with this, I would be very impressed, but I'm not necessarily expecting you to. And that's why I even wrote here, like, how are we supposed to know that? Well, this is going to be the first major topic we learn about, the substitution rule for integrals, for antiderivatives, that we're going to talk about, well, not next video, but pretty soon. But for now, I will just leave it to you to take the derivative of this function and make sure that you get back the little f function that I gave you to start with. Can you just make sure that that derivative works out? By the way, you should find yourself using the chain rule. So when I said we're going to learn the substitution rule soon, this example is going to teach you by example how the substitution rule is essentially the chain rule for derivatives, but backwards, for the backwards problem. So make sure you can make sense of all of these. Make sure you can take all of these functions, capital F here, and take their derivatives and see that you end up with all the functions little f over here. And try some other problems on your own. Make up some example functions and see if you can find their antiderivatives. And then graph the two of them and see if you can make sense of that. The next video we'll come back and talk about how this relates to the area problem, problem number 3 that we started with. That's all for now. I'll see you there.